Welcome to This Explainer. Today, we're diving into something wild. We hear so much about the digital world, right? Artificial intelligence, clean energy, advanced robotics. But this global race for the future, it's actually a deeply physical race for rocks beneath the ground. So we're going to ground ourselves in the literal, physical realities that make all our futuristic tech possible. Let's get right into it.
So, let's kick things off with a quick question to set the stage. Take a second and really think about this. When you hear the phrase, most valuable resource of the 21st century, what immediately pops into your head?
You probably thought oil, given its massive history. Or maybe gold. Heck, if you're thinking like a modern techie, you absolutely guessed data. But nope, actually it's none of those. The most valuable resource of our current century is something quietly powering the smartphone sitting right there in your pocket. It's all around us in tiny amounts, yet it completely dictates the future of global industry.
Section 1. The Physical Digital World.
It's honestly mind-blowing when you look at the sheer range of high-tech gear that just flat out wouldn't work without rare earth elements. Think about a modern electric vehicle. Its motor relies on these incredibly powerful permanent magnets that have rare earths like neodymium and dysprosium inside them. That's what lets the motor give you that instant torque and high performance while staying super compact. And it doesn't stop at cars. A single offshore wind turbine, that can need hundreds of pounds of these rare earth magnets just to generate electricity efficiently. We're talking about the literal building blocks for fighter jets, radar systems, and the advanced semiconductors that make artificial intelligence possible in the first place.
And this brings up a contrast that we completely overlook all the time. We always talk about the cloud and AI like they're these magical, weightless things just floating in the ether. But actually, scratch that. Our virtual future is incredibly heavy. The digital economy doesn't begin in the cloud, it begins underground. Building just one AI data center takes massive quantities of copper, aluminum, steel, silicon, and specialized minerals. Every robot, every sensor requires resources pulled from all over the globe.
Moving on to Section 2. What exactly are rare earths? Here's the funny thing. The biggest paradox here is in the name itself. Rare earth minerals aren't actually rare at all. They're pretty abundant in the Earth's crust. The true hurdle and what makes them the ultimate strategic resource is that finding them all bunched together in a way that actually makes economic sense to mine, that is incredibly difficult. And even worse, separating and processing them into materials that are pure enough for modern manufacturing is just a brutally complex chemical nightmare.
Which brings us to Section 3, the processing bottleneck.
So, mining the raw ore out of the ground happens in several different countries today. But raw ore on its own is kind of useless because all these different elements are stubbornly mixed together. And that is the real choke point: processing and refining. Decades ago, China saw this coming and went all in. They didn't just invest in digging the stuff up. They invested heavily in the insanely complex chemistry needed to separate and refine it. They built the facilities, trained the specialized engineers, and mastered the whole process of turning raw dirt into pure, usable tech components. Because spinning up that kind of expertise takes years, China remains the absolute heavyweight in processing. It's a huge bottleneck. Remember the semiconductor shortage during the pandemic? Yeah, when car manufacturing totally stalled and you couldn't get your hands on new electronics? That fragility was a massive wake-up call. It showed us exactly what happens when the whole world depends on a single, super-concentrated supply chain for critical parts. One natural disaster, a trade dispute, or any kind of geopolitical friction, and boom, you instantly lose access to the materials that keep modern manufacturing alive.
All right, Section 4. The Geopolitical Race.
Because of those risks, governments everywhere are now absolutely scrambling to build out resilient, diversified supply chains. The U.S. is throwing investment into domestic mining, processing, and recycling. Australia is ramping up production from some of the biggest deposits on the planet. Canada and Europe are heavily backing new exploration to secure their own networks. And Japan? They've spent years pioneering ways to reduce their dependence by diversifying where they buy from and through sheer technological innovation. The whole goal isn't just about mining more rocks. It's about making sure the global supply chain can actually take a hit and survive.
We are basically watching a massive shift in how the world operates. For a century, the global power map was drawn with oil reserves. Now, that map is being completely redrawn with lithium deposits, rare earth mines, cobalt, nickel, and graphite. Defense planners, economic ministers, they all realize that having access to these specific minerals is what's going to dictate military readiness and energy security moving forward. Geology has literally become geopolitics.
And finally, Section 5. Mining for the Future. So how do we actually fix this and build a secure future? It's a multi-step playbook. Step 1 is advancing our own complex processing capabilities so we can relieve that massive bottleneck. Step 2, obviously, is extracting these resources responsibly. But step 3 is where I think it gets really cool: recycling. Just imagine the billions of old smartphones, batteries, and electric motors sitting in junk drawers or landfills right now. Recovering the rare earths from those dead electronics could become a huge secondary source of materials. And step 4 is engineering alternatives, literally designing new motors and batteries that just don't need as many rare earths to begin with.
Okay, this is probably my favorite part. It's a massive twist of irony. The exact same artificial intelligence that is driving this insane demand for physical infrastructure and critical minerals, it's actually being used right now to solve the problem. Machine learning models are helping scientists crunch massive data sets to find completely new material combinations. They can simulate complex chemical interactions in a fraction of the time it used to take human researchers. So yeah, the very tech causing the demand is currently being tasked with getting us out of this mess. How wild is that?
When you zoom out, history really has a way of repeating itself, right? Every major leap forward for humanity has been tied to a specific resource. Coal powered the Industrial Revolution. Oil gave us the automobiles and aviation of the 20th century. Semiconductors completely fueled the digital revolution. And now, rare earth minerals are the defining physical requirement for the next era, the age of electrification, automation, and AI. They're the new baseline for everything.
So, I'm going to leave you with this final thought. We spend all day staring at screens, living in this increasingly wireless virtual world, right? But every single breakthrough, every cloud server, every AI model still begins with a rock beneath the ground, a mine in a remote desert, a refinery turning raw dirt into advanced components. No matter how virtual our future feels, the nations that secure the physical foundation of those materials are the ones that will actually build tomorrow's economy. Keep that in mind the next time you pick up your phone. Thank you so much for joining me for this explainer, and keep your eyes on the physical world behind our digital one.